We can start. Okay, perfect. So today we'll cover the upgradability and large-scale smart contract architectures. And starting from, we'll discuss the problems which actually inspired us to bring the upgradable contracts. Where first one is that smart contracts can be updated once they are deployed. The second problem was that it's impossible to fix any bugs, add new features, develop the whole product, which is also very bad. The third thing is that it causes a lot of bugs or security exploits, which can lead to loss of users, loss of funds or any tokens held by users, loss of the state. And we can all agree that requirements change, market change, like entropy increases, and software, much like biology, is in constant state of flux. The most successful software is the one that adapts best to a changing world. Keeping that in mind, we can all agree that smart contract isn't so smart if it can't evolve over time. Moving forward from this, we'll cover the basics from the upgradability and like how delegate call and the internal transactions work. So imagine having a user who is sending transaction to a contract, like calling a function, which goes directly to the upgradability proxy contract, which then just delegates call to the actual implementation where the version is working and performing all the logic, which does the logic but writes the state to the actual proxy contract. So we have one contract which is literally codeless, and we just have state on it. On the other hand, we have the implemented version which performs all the logic, which is amazing. Moving forward, we have this design pattern, which is made of upgradability proxy again, which is the only contract that operates in our case, and that contract practically works as our storage in every case. On the other hand, we have imagine contract A, B, and C holding the actual logic implementations, and they're inheriting the upgradable pattern, which has to follow this upgradability storage structure in order not to mess up the EVM bytecode. So if we all agree that upgradability storage, it practically just saves the implementation address where we'll delegate call to our proxy, and proxy just contains the getter of the current implementation and delegate code method. Moving forward, we have the eternal storage upgradability pattern, which we applied to our system, which is we can say it's enterprise level system on the blockchain, which has on two sides we have covered this middle picture. On the left, on the right, we can focus on those logic implementation and logic and storage implementation. They both have some mutual structure they are inheriting, which is the pointer to the manager contract, which is our singleton registry, and pointer to the proxy storage contract. On the other hand, the storage implementation has to implement this generalized storage structure, which is created in a way that it can store either primitive or structures, like complex data types, such as key value pairs. For instance, primitive key generation should be just the hash of the variable name. For the mappings, we can just do the hash of the name and the key we want the value for. For the arrays, it's enough to hash the whole array and then get the whole array always, and then go through it. So more or less, that's how it should look in the way. Also, there are generalized getters and setters depending on the type of variable we want to fetch. And the very important thing is that just a logic contract, like proxy logic contract, is permitted to write to the proxy storage. So we can assume that we have proxy logic, which is the only one who can update anything in the storage, and of course everybody can read from there because it's a blockchain and everything is public. Moving forward, every new innovation has some pros and cons. Let's go firstly through the pros, which are, let's be positive. So the live decentralized application, it can be continuously expanded with new features, which is amazing. And adding to that, the bugs can always be fixed. So every bug we found or catch, we can fix it and just release the new version with keeping the state. Data can be read from the contract normally, And the data structure used in data contract can be updated and added too. So we can continuously modify our storage and expand it, which is again amazing. On the other hand, there are consequences that smart contracts are becoming trusted. They were trustless, now they're trusted, unfortunately. There is a loss of decentralization. Also a big con that they need to be separated into logic and proxy storage contract, which increases code base a lot and complexity of the code. And that reflects an increasing number of internal transactions, which is bad in terms of gas costs. Moving forward, and keeping in mind that every problem has its own solution, we can literally going through the upgrade process explain how we solved a couple of the consequences mentioned in the slide behind. So firstly, contract upgrade process is contained of 3 steps, where the first step is deploying the new contract version and the actual code or implementation, which can be done by anyone who has the access to the code base, because this is a blockchain, so practically everybody can just perform a transaction and deploy a contract. Then we have the option to add that address, that implementation address, as a new version to our manager contract. And here we apply the first layer of security, so we are restricting that only to whitelisted maintainers, so we can avoid spam and keep version numbers in order. And like those 2 steps are pointless without the 3rd step. So the actual upgrade of the contract and changes in the running contract happen at the moment we upgrade proxy through manager to redirect calls to that version, and the second layer of security is applied there, where it can be done only by DAO or decentralized autonomous organization, which is by design keeping a bit of decentralization and keeping the contracts trustless. Moving forward, we'll just cover that we succeeded applying this pattern to really big software, and it's contained of 3 layers. And the first layer is the smart contracts, of course. I intentionally took this Tuki Singleton registry out of the context because it's important to say that it has management and it sees all the contracts in our system, either singleton contracts or non-singleton contracts, as we call them, ephemeral contracts. There is then second layer, which is called Tuki protocol, and it's holding all the cryptography which we need in order to perform, in our case, multi-party state network, and to do a lot of things off-chain. And as well as it holds the build files, ABIs, addresses, and it takes care of the CICD whenever some either update or hard redeploy or soft redeploy system is happening, which is such an amazing thing. Where then, whenever we do a kind of the redeploy, we generate the new ephemeral hash, and then we have the web app, which downloads a specific version of the Tuki protocol from IPFS, depending on the non-ephemeral hash generated at that moment of the campaign deployment or actual ephemeral contract deployment, because we wanted to keep ourselves available to continuously add new features to our non-singleton contracts and implement them like for a long distance. So whenever we decide to bring some new feature, we'll just add it to the code base, deploy new version, and then every time new contract is deployed, it will follow the newest ephemeral hash, and the web app will load depending on that. Moving forward, just to mention the Tuki network singletons layout. So we have a Tuki Singleton registry, which is the manager for the whole upgradability system, and that contract practically stores all the necessary addresses of the proxies of all our contracts. Either they are singletons or non-singletons. They're all stored there, so our singleton contracts communicate with each other by every time asking Tuki Singleton registry for the active proxy address of specific contract. By that, we avoided so all the addresses are stored in a single point of storage, which will allow us to, whenever we want to update some contract or to change it, we will not be supposed to send like 5 transactions or 10, depending on how many contracts has pointers to that contract to save the new addresses. Instead of that, we'll just make it on one single point of storage, and all contracts will dynamically get the newest version. So those are about the singletons. Just to mention about the ephemerals. they are stored all their versions are stored in the manager, which is the Tuki Singleton registry contract I mentioned in the slide below. And deployed campaigns, deployed ephemeral constructs, they're not upgradable. They are working as a proxies, which will delegate the call to the active logic implementations at the moment of the contract creation, which will be wired to a specific ephemeral hash at that particular moment. And whenever a new stable version of campaign is ready, that's what I've been explaining about, that we want continuously to update our system and bring new features. It will just set new addresses as valid ones, and every campaign created after that moment will use the latest implementation, which will follow the non-ephemeral hash. And that hash is, just to mention, generated by SHA hash of the bytecodes of all contracts which are taking part of that particular ephemeral. For instance, in our case, we have campaigns, Tuki campaigns. They can be acquisition campaigns to sell tokens, donation campaigns to bring some donations. And they're all very important because, for instance, we are keeping all the state in the contract and a lot of data, so we needed a couple of contracts to store it and to maintain it, to keep all the layers of security. In order of that, we're deploying, for instance, for acquisition contracts, we're deploying 4 proxies to point to 4 different contracts, and by that that's why we are using this SHA of all bytecodes of those contracts. And also, as mentioned before, web app will load specific version of Tuki protocol depending on that ephemeral hash. Just to mention how the creation of those ephemerals work. So, for instance, there is a contractor who would like to create some campaign to, for instance, to sell some tokens. So he sets some parameters like start date, end date, what's his goals, etc. Sends the Tuki protocol, which wraps up all the data into one transaction, which goes to Tuki factory, which will firstly call Singleton registry to query its state and find the all actual current active versions of those campaigns and give them back to the factory, which will later on deploy the proxies, point those proxies to the specific implementation addresses, and those implementation addresses will on themselves, while deploying the proxies and calling such as a constructor things on them, will do validation of those params, which after it's done, we are sending that, like, the main proxy of the campaign to our campaign validator contract, and that contract is in charge to validate that all the contracts were validated properly and to mark that campaign as whitelisted. So our pool of singletons is closed, and the only way to interact with them, with a couple of functions there, is to have it whitelisted, which campaign validator does. It stores all the whitelisted addresses. Moving forward, it will return that information to Tuki factory, and immediately after we'll deploy the event through Tuki event source, which we wanted to keep all the events at the single point of storage, so we can then use GraphQL to query the state and perform some data operations over the events emitted. Just to mention, this is done on the very big repository, which includes 125 contracts, around 11,000 of Solidity lines, 13,000 of Tuki protocol TypeScript lines. There is currently 206 test versions released, 89 staging versions released. There are 2 types of singletons, as I mentioned. There is upgradable, which is there's total of 32 contracts, and non-upgradable, which is 3 contracts. 2 types of ephemerals, acquisition and donations, retrospectively 4 and 3 contracts, and 3 repositories maintained in this level. And all this is mentioned just so we can be more descriptive, and so you can understand on how big repository we succeeded applying this pattern. Regarding the CICD in smart contracts, so there is in our case, hard redeploy, where we'll just reset the whole system and erase all the data on the contracts. Soft redeploy, which is used just for updating specific singletons and adding new versions of campaigns. There is ledger support. Also, there is iterative process, whereas the user is available to continue if dropped. So we are archiving build. Also, we're wrapping the Solidity and TypeScript. We're always, when we do deploy, we're publishing npm package, which is stored on the IPFS, and it's used in the web application. We can generate the singleton, non-singleton hash, deploy hash. We have deploy config, and all the stuff which is done whenever we deploy something, there are bots alerts on all repositories currently we are having. Just to mention, we apply this system, and this is on the top of it. We have the 2-key link, we call it Smartlink, which is contained of the code hash, specific JavaScript and TypeScript code, which we download from IPFS, and which is the decentralized file storage, just to mention. And we have the state hash, which is actually the 2-key protocol state at that particular moment. So if you want to experience this live, you can scan this QR code, and you'll see your sign-up campaign running, and you can get free some Robston 2-key tokens deployed on the Robston. If there are any questions, don't hesitate to ask. Nothing. So? Oh, okay.
Can you explain more about the 2-key campaign validator mechanism you mentioned before?
Yes, of course. So going back to here, let's say we have a closed pool of the singleton contracts, and there are sensitive functions which we want only proved campaigns to have interaction with. So campaign validator is just a contract which has a specific input, and regarding that generates specific output. What I want to say is that only access to validate campaign function, for instance in campaign validator, is through 2-key factory. So everything has to go through 2-key factory, calling the campaign validator, then it does a couple of queries over the state of the newly deployed contracts, make sure it's all okay and all data is valid, and then once it's done, it whitelists that campaign that it can interact with the pool of singletons, update the reputation, etc. So, yeah, by the way, my name is Nikola. I'm heading the blockchain research and development at 2-key for more than a year. Currently here for the blockchain week, and especially this Ethereal event. Thank you everyone. It's nice to have you here.